Um, Hello and welcome to the second in a series of webinars being presented by the Electricity Sector Climate Information or ESCI Project. For those who haven't been exposed to the project, the ESCI Project is funded by the Department of Industry, Science, Energy and Resources and is undertaken by CSIRO and the Bureau of Meteorology in conjunction with the Australian Energy Market Operator, AEMO. My name is Rebecca Gregory and I am the CSIRO Project Manager for this project. Before we get started, I'm just going to mention a few housekeeping items. As you can see, you've all been muted and your videos are turned off. It's just to reduce feedback and distractions for the presenters. But please use the chat function on the Zoom toolbar to ask questions throughout the webinar, and these will be answered by the presenters during a Q&A session at the end of the presentation. And since we have two presenters today partway through, we'll address as many of these as possible. Today's webinar is entitled ESCI Case Study, Heat Impacts on Variable Renewable Generators, and is being presented by Ben Jones from AEMO and Judith Landsberg from the Bureau of Meteorology. Ben's a forecasting specialist with AEMO who currently works to incorporate climate and resilience considerations in longer term planning processes. He is a key ESCI project team member and collaborates across all components of the ESCI project. Judith is the ESCI project coordinator and leads the project delivery to the department whilst also working across key project areas. She's previously run a sustainability charity and coordinated major renewable energy projects. So on that note, I'm going to hand over to Judith to start the presentation.
Thank you, Beck, and welcome everybody. Let me just start off by sharing my screen. So hopefully you can all see the slideshow. We renamed it slightly from the original communication just to try and be clearer about what we want to do today. So we want to use the opportunity to introduce the project and the key information output from the project. And then Ben will walk through a case study that we've used on how the project outputs can be used to do a risk analysis for some infrastructure for the electricity sector. See if I can actually, just a disclaimer, this presentation is just to illustrate the risk assessment, a risk assessment based on data output from the project. The data output is preliminary. The output will be made public and will be available for industry risk assessments, but what you'll see today is not intended to be guidance for any decision making. The project itself is a collaboration, as Beck said, between the Bureau of Meteorology, CSIRO, AEMO, and the Department of Industry, Science, Energy and Resources, although it's actually funded by the Department of Agriculture, Water and Environment. It's a $6 million project over 3 years. We're just over halfway through. The goal is to improve climate and extreme weather information and is part of the government's response to the Finkel review. At the end of the project, and hopefully as we develop the information on an ongoing way, the project will make existing climate change data and information more accessible, and will also work with industry to understand needs and to provide some tailored climate information, which I will also be talking about. The start of the project and part of the efforts in the first half of the project was an understanding of how the national electricity market is vulnerable to climate change, and so where in the decision-making processes climate change should be taken into account. What you have in front of you is what we identified as key hazards for the sector. So temperature is a key hazard, particularly as under climate change is expected to increase. And the electricity system is vulnerable because of reduced generator and network capacity and increased failure rates at the same time as there is increasing customer demand for cooling load. Heat will also reduce rates of electricity asset deterioration and failure rates and increased maintenance and replacement costs. And that's why we've focused on heat today as the first hazard, partly because there's a fairly clear climate signal but also it is integral to the performance of a lot of the electricity sector infrastructure. We have heard from stakeholders that bushfire is also a key hazard. It poses a physical threat to all assets, and a particularly high operational risk to the transmission lines, as smoke can cause sparking and heat can cause derating. Bushfire risk also requires consideration in line route and selection, and the design of interconnectors to try and reduce the risk by increasing geographic diversity. Wind is also a hazard. It can clearly affect wind generation output, which can have an impact on the investment case and on the return on investment through plant profitability and design, and how the actual wind farms are designed. Ben will talk a little bit about that as well. It also requires consideration from a network capacity point of view as to whether the system can maintain its strength as wind varies, and may eventually require changes to design specifications and how failure rates are modeled. The fourth hazard is precipitation and dam inflows. This not only reduces water available for hydro generation, but also has an impact on thermal coal plants because it reduces the cooling water that's available. There's also a second order effect on the network because it's likely that if there's increased drought or reduced seasonal precipitation, then it increases the requirement for desalination loads, which again is an important planning consideration. Coastal inundation is a hazard that's been identified as really important for parts of the network, particularly where there's low-lying generation, distribution, and distribution transmission assets may be impacted. That's a lower priority for this project, partly because it doesn't tend to be a system-wide hazard, and partly because some of these hazards can be, some of the risk can be assessed by looking at sea level. But we still want to acknowledge that it's certainly a hazard for the whole of the electricity market. What we're doing in the project is very much taking a decision-focused approach. So we wanted to look at industry processes and current industry decision-making for which a climate assessment is appropriate and should be included in the risk assessment. We looked at this at a pretty high level, looking at three kinds of risk. So a risk to the reliability, a risk to investments, and therefore inclusion in business cases, and an operating risk and power system resilience effects. So the reliability risk is measured using unserved energy and is modeled by AEMO. It's also important for the transmission companies who look at the value of unserved energy when they're making their regulatory applications for increased investment, and for the distribution companies, and which use metrics such as the system average interruption duration index and system average interruption frequency index for their asset management and planning. Both of those will be affected or can be affected by climate and weather. Investment risk was our second target, because if assets for which weather is a fuel, such as solar farms and hydro and wind, if they don't perform in the way that's expected, then that's obviously a risk for their investors. But similarly, both AEMO and the large network service providers have an obligation to consumers to have prudent investments. And finally, operating risk and power system resilience is primarily looking at generator and network specifications, how the assets are managed and how the system operates, particularly when it's at points of stress. So in response to the work that we've done looking at vulnerability and looking at decision-making processes, the ESCI project has been delivering tailored climate information that will support decision-making. Some of these we've already produced, and some of these we will continue to produce over the next year, which is the duration of the project, due to finish next June. So we're looking specifically at the hazards I mentioned: the temperature, the wind, the bushfire and precipitation. And the kind of climate output that we're providing, firstly, is trends in climate variables, which will affect supply and demand. So this trend information is in the form of time series with temporal and spatial resolution, which is appropriate for the sector, which can be put as an input into supply and demand models, and also into investment models. The second kind of climate information is high impact weather simulations. So the project has been asked to provide synthetic, compound, or coincident extreme synoptic weather events. So that's an awful lot of adjectives. So what it essentially means is that we are modeling extreme events that are plausible, that we can find in the climate projections, in order to provide information that can be used for stress testing or for testing resilience investments. And I'll give you examples of these in the next few slides. The third category is regional thresholds for key climate variables. So some assets, such as solar panels, have a fairly rigid threshold over which they don't perform very well. And so what we are supplying is probability of exceedance for some of these key climate variables. And as I said before, these will be inputs into the long-term risk and decision-making planning for the network. Long-term, what we've been asked to provide is 2030 to 2060, although when we do climate model, we're taking it all the way from the present up to the end of the century. But that window is clearly within the lifetime of most electricity asset planning and operations. So I'm just going to spend a couple of minutes walking through each of those kinds of climate information so that you get a feel for exactly what we are hoping to provide. I also want to make the point here that we're halfway through the project, and a lot of what we're doing in the second half of the project is testing this. So we welcome feedback from any users, any people who intend to use or would like to use this information. We are entering a user experience phase of the project, and where we're trying to match up what climate scientists are producing with how the industry uses this information in models. So the first kind of climate information I talked about was trends in key climate variables, which affect supply and demand. The project is providing time series looking at 171 sites. As you can see, they pretty comprehensively cover the national electricity market, as well as key sites in other parts of the country. The information is based on, uses right now 6 GCMs, so 6 global circulation models for climate simulation, and depending on timing and resources and access to high-powered computing, then we will include more of the GCMs. So, and are providing, as I said before, information tailored to the temporal and spatial requirements of the grid. So 30-minute simulations, starting in 1980, so we can match up with history, and taking it through to 2060, using a high emissions scenario. So that's the IPCC representative concentration pathways, so that they can genuinely be used for stress testing. All relevant variables are simulated in these time series. So dry bulb, wet bulb temperatures, humidity, wind speed and direction at both at ground level and at the heights relevant for wind farms, 150 meters and 250 meters. GHI and DNI, global horizontal irradiance and direct normal irradiance for solar farms, cloud cover, precipitation, and forest fire index, which is a derivation of a number of these variables. So the time series maintain the relationship between all these variables. To give you an example, and from this you can see the high temporal resolution. So this is at one site on the Murray River. It's a projected time series that starts in 1980 and takes it through to 2060. And you can see the high natural variability. So, and what you see is the spikes of the 30-minute temperature resolution. And you can also see from that the trend, the temperature trends at this site. So at the highest level, the temperature trend in 1980. This high percentile was just below 40 degrees and is expected to exceed it by 2060. To give you an example of the high impact weather simulations. So what the team has done is to take a Black Saturday-like weather event and see what that might look like in the future. Just for comparison, this is taken, Black Saturday was 2009. The gray at the top is weather that is over 48 degrees. The light purple is 46 and the dark purple is 44. Sorry, those scales are probably rather small for many of you, but you can see that starting in 2009, in the Black Saturday event, this is 2009, 2014 give you the historical information, where you can see that very intense heat wave over southeast of Australia. And the projection that we've used in 2045, you can see the heat wave not only is significantly more severe, it involves much more of West Australia and also Southern Australia. And actually, it's also worth noting how the eastern seaboard, the very high temperatures in this climate projection come up the eastern seaboard here. I would like to point out this is not a forecast. We're not expecting this to happen in 2045, but the importance of using of looking in the climate projections for this sort of extreme or compound event is to say that this is plausible. This is an event that could happen in the time frame we're talking about. And the other value of this, of using the climate projections, is that we can look at the weather patterns that are associated with that. So this particular scenario that we have developed, you can see there's a strong frontal system that in 2045 that comes over Australia, that southeastern Australia, that will drive, would be expected to drive very strong winds, and then which is the pattern that was associated with Black Saturday and Ash Wednesday. So that drought followed by heat wave followed by very strong winds are the conditions that is very likely to create catastrophic fire weather. So we are providing this sort of, this information so that it can be put into the quantitative modeling by AEMO and other stakeholders and can be used to see what then happens to the assets. So I'm not sure if you're all going to be able to see that, but just to show you what it looks like, this is the simulation. If you can see the animation, you can see successive hot days shown up with the very hot, it's not on the same, very hot temperatures and a cold front coming across Australia very rapidly over the space of a couple of hours. And as I said, it provides coincident variables, temperature, wind, humidity, and precipitation at all of those locations. The example of the third kind of climate information we're providing. So these are temperature maps. Ben will show you some more examples of those. The one at the top is history. So this is 1961 to 2020. And it shows you what the 10% probability of exceedance, so 1 in 10-year temperature was. The four charts on the lower half of the screen give you the projected POE, 10% POE, and you can see this very hot band is this yellow, yellow-green at the top, and although there is variation in the climate projections, all of them are projecting that the 10% POE will increase. So you can see one of the reasons I wanted to put this up is to show you why we're looking at an ensemble of global circulation models, because they will give us slightly different spatial information and slightly different estimates of what will happen to the temperatures. What we're doing in the ESCI project is we want to demonstrate, to test how this information can be used by the sector. So whether we are providing information that is actually helpful for decision making. And so to do that, we're going to do 3, and we hope if we have time and resources, 5 case studies. And I want to just emphasize again, this is not a recommendation. The case studies are not going to provide guidance on how you should adapt. They're a test of whether the information that we can provide will help people's decision making. So the first one is the projected impact of extreme heat on generator ratings and performance, which Ben will walk you through. We're also in the process of developing a case study around the projected impact of bushfires on transmission lines, which is primarily about how you choose the routes to get geographic diversity and reduce risk. The third one will be on the projected impact of increasing wind gust frequency and magnitude, and whether we are able to identify whether the transmission line failures will increase. One of the challenges for the projects is some climate trends like temperature are pretty clear and quite well characterized, and some climate trends like some of the wind information are because of natural variability and the physics behind them, it's actually not always clear that we can say whether there'll be an increase or decrease. So part of what we're testing here is what information we can provide. The fourth case study that we would like to do is a coincident heat wave across all of the major load centers. This is not something we've seen in history. It is something that requires modeling in order to provide the quantitative information necessary for investment decisions. And the fifth case study is looking at the projected impact of decreasing precipitation on hydro generation. And so some of the decisions around sequencing hydro output or using hydro for to supplement when mainland when renewables in the grid are not generating, and how that might be affected by reduction in precipitation. So that's the end of my walkthrough. Let me go back to these. The ESCI project, but I thought we'd pause here for questions. Becca, I can't actually see the chat, so if you'd like to let me know if there are questions.
There's no questions at the moment, so if anyone wants to put any in the chat, we will ask them again at the end.
I might just leave it for a minute to see if anything comes up.
Case study 2, come up wide transmission lines, but not distribution lines.
We're actually just using the transmission lines as an illustration, partly because the spatial resolution of forest fire danger index is quite high. It doesn't have very high resolution, and also we can't model actual bushfires. We can model forest fire danger index, but there are a lot of other factors that go into actual bushfire ignition and whether they have an impact. We've chosen to look at transmission lines because this allows us to look at all of the factors that go into it, but the intention is to provide a model that could be applied to others as well. Does that answer the question? Ben, do you want to add to that?
Yeah, the only thing I'd just add to that, Mark, is we've been working on the bushfire case study for probably 6 weeks now, and we do have some working group members from say AEMO Victoria Planning and Electronet Planning. So we're really looking at, given that there are some proposals to build new transmission lines through Victoria and South Australia, how should we site those lines in a way that minimises bushfire risk and minimises the probability that multiple lines are impacted at the same time. We're actually quite confident, though, that the framework that we've developed would be directly applicable to distribution planning as well. So as we kind of finish some of the prototype analysis and go into consultation, which is what we're planning for July, we'll certainly be engaging with quite a lot of distribution network operators to identify the applicability of the analysis and the model that we're proposing.
Thanks. Can you hear me?
Yes.
Okay, yeah, I just want to remind you that in the last bushfire season, transmission was hardly affected and distribution was severely affected, through several networks. And the the usefulness of the model will be quite different for transmission and distribution. I'm sure, I just wanted to check that you've taken this into account, that it's not about where you put the lines. It's more about whether you put the line somewhere or take communities off grid onto microgrids or standalone power systems. So it would need to be robust enough to handle that kind of different business case.
I think the analysis ideally would go that, and I suspect your perspectives on the mitigation solutions will be reflected by others as well. So yeah, we'll definitely be commenting on, in terms of these case studies, they don't make recommendations around what the adaptation options should be, but through the interview process and the consultation, we typically identify a range of adaptation options, and I'm very much certain that will be part of the suite of available options for mitigating the risk.
Thank you.
Becky, I've just realised I can see the chat, so I can respond to these. Sorry about the technological practice here. So Dan, can we comment on the selection of GCM ensembles and why these? Yes, more would definitely be better, and we will get through as many as we can for the project. There will be, I am not a climatologist, so I can't comment on that here, but it will be included in the guidance material for the project. So details on the methodology, why the GCM ensemble was selected and which ones were used. Similarly with the RCPs. What I will say is that we're being guided by Climate Change in Australia, which is a joint product of CSIRO and BOM, recommend 8 GCMs, and so those are the ones that we are using to guide the study. Scott, at what depth are we projecting our simulations? Are we looking at microclimates? Are we looking at regional trends? We are downscaling, well, the climate scientists are downscaling to the extent that they think that the information is realistic and depending on what is needed. So once again, I'm not entirely sure what you mean by microclimates, but in some cases, like of the urban centers or next to topographical features, then the downscaling will take those into account. And then I can't remember exactly what, so 1.5 kilometers resolution in some places, and in other places it's 5 or 10. Is that correct, Ben? Do you remember?
Yeah, even 12 kilometers. I suppose it all comes down to the particular problem that is being solved at the time. I think we've got guidance around from the climate scientists, which will be embedded in some of the final outputs of the project around what is the methodology you should be using to select climate products. And I think you would select a product which is best fit for the problem that you've got. And going back to the GCM question as well, we've certainly been given guidance that you want a selection of GCMs, but also a selection of downscaling techniques, which would allow you to test the bounds of uncertainty and understand kind of what a best case or middle case and worst case might look like in the future to assist in decision-making processes. If you had a problem that really required microclimates, it'd be interested to see how you could use history and some of these climate projections to answer that question. Although we would probably say for the granularity of the problems that we're solving, whether that be wind farm or solar farm or demand, the types of downscaling that we're seeing, whether that be 10 or 12 kilometre grids, seems to be perfectly adequate.
The other thing that I will add is that it depends on the variables. So some of the climate information that we want to provide from the projections, as I said, the temperature trend is probably the clearest and can be downscaled with the greatest resolution. And there will be some climate, important, climate events that actually all we can provide is really broad regional information. So an example of that would be that the indication is that cyclones are probably going to be less frequent, possibly more intense, and possibly more southward track. And that may be the level of the information that we can provide for the sector. So the climatologists in the guidance material, the intention is to be as precise as possible with explaining what we've chosen, what we can provide, and what the probability and confidence is for those. There'll be another opportunity at the end for questions, but if there's nothing right now, I'm going to hand you over to Ben, who will walk us through the ESCI heat case study.
Yes, thanks, Judith. I think it was really important we went through some of those higher level concepts as to why we're approaching things in a particular way first, because as Judith started at the very beginning, can you go? Yeah. The purpose of this case study is, while we hope that the results will be indicative and useful of where climate impacts are going, the major purpose as to why we're doing these case studies is to demonstrate and test the risk framework, the guidance material, and really identify whether or not the information that's being provided as part of the project can be integrated into electricity sector decision making. So in that context, we're presenting the case study in line with the risk framework, where this particular risk framework identifies a 6-step process, which is similar to many other risk frameworks which exist, which is to first start by understanding the context or the problem that's involved, which is identifying the decisions in the electricity sector which are susceptible to climate risk and identify which stakeholders. 2, move towards assessing the impact and identifying the risk, identifying the relationship between the vulnerable assets and the climate variables, applying future climate projections and quantifying risk. And then 3, moving into identifying adaptation options. Noting that the colours indicate that steps 1 and 2 are really the focus of ESCI, the focus of identifying the context and moving towards quantifying the risk. And the case study will go some ways towards identifying adaptation options, or at least listing and documenting the adaptation options which were identified through the case study. But really beyond there, it's up to the organisation in question to implement this into standard business process and standard risk management process to identify the adaptations, to make decisions, to implement the risk mitigation solution, monitor, evaluate, adapt, and then restart the risk management process again. So the case study steps through these processes as 1, 2, 3. Early in the project, we did quite a lot of vulnerability scans with industry participants to understand what were the risks that the sector perceived to be the largest risks arising from climate change. Heat impacts continually came to the top of the risk vulnerabilities because it touches on so many parts of the electricity sector, but one particular one was identified, being that both solar and wind farms are known to be impacted by heat. So we want to explore what that relationship looks like. So we know that wind farm output is predominantly a function of wind speed, but it's also affected by temperature. We know that solar farm output is predominantly a function of solar irradiance, but is also affected by temperature and wind speed for that matter. And those vulnerabilities, i.e. that relationship with temperature, results in 2 different types of risks to the sector. So going back to the 3 types of risks that Judith identified earlier, being temperature may affect the reliability of the system. And by reliability, we mean the ability of the system to meet the needs of consumers. So if it's not reliable, it might result in emergency generation, procurement, or potentially outages. And also that the vulnerability has the potential to impact investment risks. So if temperature materially affects the volumes that are being produced by these wind and solar farms, then investment owners might be impacted by reductions in revenue. Go to the next one. So moving beyond the impact or the risks in question, we started to try and understand what that impact could be. And the first step in doing so was to try and build out that relationship to understand how temperature affects the thing in question. So in this case, the output of the generators. So the plot on the left shows the relationship between irradiance and output. And when we say normalized AC output, we mean output divide capacity. And it shows also how that output is affected by temperature. So these relationships are quite well known, widely available, and easy to model. You might expect a site to reach about a 1,000 or 1,200 watts per square meter on a good day. So therefore, if you were to look at that, say, purple line, the third one from the top, you get a pretty good understanding of how a solar farm will derate as temperature escalates, with the most substantial derating occurring beyond 50 degrees Celsius. The model on the right, wind models are far less readily available, and I think this is because each wind farm is quite different from another. Unlike solar farms, which are all quite homogeneous, every wind farm is a little bit different in the way that it responds to temperature, and it's quite different in the way that it responds to wind, and extreme wind for that matter. But what we developed is we used a collection of operating wind farms across Southeast Australia and built the empirical relationship that was being observed between wind, extreme wind, and temperature for those wind farms. So these curves are built on operational data, and don't particularly reflect a single wind farm. They reflect maybe what we would see in aggregate in response to these temperature and wind variables. Interestingly, with wind farms, each turbine tends to act independently. So as temperature goes over threshold, one by one, the turbines start to shut down, which means that we don't tend to see this on-off behavior, but we see, as temperature goes up, a continuing decrease in the net or gross output of the wind farm. You will also see a little bit of a kick there. So there seems to be a kick there at around about that 8 or 10 meters per second. So there seems to be a relationship there as well, where at low wind speeds and high temperatures, we don't see derating, but at high wind speeds and high temperatures, we do see derating. So there's a suspected relationship that it's actually the internal temperature that matters, and it requires friction from the wind to generate that internal temperature as well. But this relationship roughly lines up with the data we're observing from many of the in-service wind farms. In terms of projecting the impact, we're doing this twice. We're doing it once with a very simple assessment, which is using the POE maps, or the temperature over threshold extreme variable analysis. And then secondly, we're doing it in a more comprehensive way using the full time series data. So it's able to demonstrate from the risk management point of view how you might use those different sets of data for different purposes. In this particular example, we can see the plot of the 1 in 10 year maximum temperature, or the POE 10 max temperature for the past, and the POE 10 max temperature for the future. If we were to theoretically put a wind farm near Adelaide that had a historic 10% POE temperature of 44 degrees and a projected 10% POE temperature of 46 degrees, we can look to the normalized AC power curve for wind farm and estimate that in the past, that wind farm might have had on that day an average output of approximately 40%, and in the future that's likely to be approximately 0%. So as a back of envelope calculation, we can say under extreme conditions, the output of wind farms is projected to decrease. We've done exactly the same again on solar farms, where we've used the power curve for the solar farm. If we were to theoretically place a solar farm near Mildura, which has a historic 10% POE temperature of 46 and a future projected 10% POE temperature of 48, we can estimate that the maximum output on that particularly hot day would drop from around about 70% of rated capacity to approximately 65% of rated capacity. And I think it's worth noting that given that solar farms don't really have substantial derating till beyond 50, that we were probably expecting to see the level of derating from solar farms to be more subtle than wind farms until they breach that 50-degree threshold. So moving beyond the absolute extremes, or the 1 in 10 year extremes, we also did the approach again of risk analysis using the comprehensive data set. So in this, we've used the 30-minute CCAM simulations using a variety of different GCMs. And by doing this, we're actually modelling every 30-minute interval from 1980 up to 2060. And that allows us to look at how the generator output is changing at all different types of time intervals, whether that be over the whole year or of a period of interest, like the peak demand period. So what we've done is we've broken up the data into annual averages and peak period averages, where we've used a study period of between 12 p.m. and 7 p.m. Australian Eastern Standard Time for the top 5 hottest days of the year as a proxy for the period when peak demand occurs, which is a function of temperature, and that's also associated with peak price, and that's the period when the system is under most stress. In this particular case study, we selected 4 sites around Australia to demonstrate the different impact. A site somewhere near Adelaide, southern New South Wales, western Victoria, and central Queensland. On the graph on the right shows a small selection of what that time series looks like for a wind farm. What you can see on the graph is that the blue line represents the wind speed. So in this particular day in question, wind speed is moving between sort of 7 meters per second up to maybe 11 or 12 meters per second. But you can also see the diurnal pattern of temperature represented in red at the top, which is, this is one of the hottest days in the sample, where overnight temperatures are around about 30 degrees and daytime maximums are in the high 40s. The black line represents the wind farm output in response to those weather variables. And what we see is as the temperature reaches very high temperatures, the wind farm effectively shuts down and doesn't come back on until those high temperatures have well and truly passed. So moving beyond that time series, these graphs now show what the annual mean is of those and what the peak period mean is over a selection of GCMs. So there's a big leap between a small time series to the annual results. But the interpretation of this shows that, say that the graph on the top left for near Adelaide, it shows that the black line is the historic normalized solar farm output, which shows in that particular location, given the temperature and irradiance and wind speeds that are observed there historically, that the annual capacity factor or the annual normalized solar farm output is approximately 30%. We can then look to the GCMs or the CCAM output of the GCMs into the projections of the future, where temperature changes, where irradiance changes and wind speed changes, and see that the GCMs are roughly holding on to the same path as the history and potentially even increasing slightly as cloud cover declines and irradiance goes up. We actually see quite a similar trend across Adelaide, Victoria and New South Wales, but not quite as strong in Queensland. The lower graphs show what that same relationship looks like during the peak period. So this is the 5 hottest days between 12 p.m. and 7 p.m. per year. Now, given this is a much smaller amount of time, there should be more volatility year to year, and we are seeing that increasing volatility year to year, where the black line shows the historic output during peak demand periods per year, which range between 50% during that period up to 70%, and it should be higher because it excludes more nighttime periods. The GCMs then show how that's projected to change into the future, and overall across all 4 regions there's a very slight decline in peak period output, although because it's summer, the average output over those 5 days per year typically remains fairly high. We've done the same thing for wind. As you can see, the example of near Adelaide at the top, the annual mean shows that the wind farm in that location is likely to have an average capacity factor around about 40%, or a normalized wind farm output of approximately 40%. And the projections all show fairly consistently a slight decline in output over the forecast horizon or the projection horizon, with uncertainty attributable to the GCMs. We see similar trends in Western Victoria, although very shallow trend or nearly flat. Same in Queensland. The peak period mean is exactly the same again, and as we said, it's a smaller time period, so it should be more volatile, and we see that volatility year to year, but it's quite important to note that the average output during that peak demand period is lower than the average output during the annual mean. So as opposed to a 40% average output, it's probably starting at around a 20% average output during the peak demand periods and declining over the forecast horizon as temperatures go up. We see subtle downward trends in Adelaide, Western Victoria, and southern New South Wales and Queensland as well. So summarising the analysis that we've seen so far is that from a peak demand point of view, the 10% POE temperature charts showed a decline in output, which was supported by the comprehensive analysis during peak demand periods, but that there was a negligible change in average output for both solar and wind. But summarising output during peak temperature, peak demand, peak price periods is already low for wind and volatile with a downward trend. And for solar, the output during these peak demand periods is less volatile and decreasing slightly. Moving into the final step, as I said, the project won't make recommendations around exactly what is the adaptation pathway that should be taken, but we did quite a lot of consultation with industry to identify some adaptation pathways. Talking to investors and owners of wind farm and solar farms, we identified we asked them how material were the investment risks. We were told pretty much the reductions in output are unlikely to be material investment risks relative to other market transitions. So things like marginal loss factors and variability and uncertainty in price. But that risk could be mitigated with more robust specifications at a cost. When it comes to the reliability risk, so the contribution of solar and wind farms to peak demand supply availability, that those reductions in output during peak demand may decrease system reliability if not considered thoroughly, and that those risks arising from the declining output could be mitigated with more dispatchable generation capacity, with more transmission investments to link regions with less impact, but those mitigation options will come at a cost. Let's have a look at those chats.
Yeah, thanks, Ben and Judith. The questions from the chat, there's just a few. The first one says, how does the temperature impact the wind farm output due to the derating efficiency of wind turbine converters? Could you provide an illustration of the wind turbine converter characteristic against temperature?
I don't think I'm the best person to answer if that's more of a mechanical question of exactly how do wind farms derate. I think we have a pretty good idea of the way that that solar farms derate and the physics behind that. When it comes to the wind farms, I know that through talking to manufacturers that they do have options available to them to build in more resilience to temperature, so they can design particular cooling features within the wind farm. But the actual mechanics of it, we know that there's a relationship there with the friction caused by the movement and the ambient temperatures working together to cause a derating effect. Although I can't speak to the physics of exactly how that occurs. I can certainly say that in the 2020 summer we observed quite a few wind farms that derated more substantially than we expected as a function of temperature. It's definitely occurring. The physics of why, I can't answer, I'm sorry.
Thanks for that. The next question was, is the 50° plus derating likely to be associated with inverter operating temperature thresholds?
Absolutely. So there were two parts to the curve. There's the DC derating and the AC derating, where the DC derating occurs through the the panels themselves, and then the AC derating occurs at the inverter point. So both of them derate at different thresholds in different ways, and the curve that we presented, particularly the 50-degree cutout, is the inverter cutout.
The last one that I can see in there is, could you please explain the factors that lead to wind farm shutdown during high temperature period? Since during high temperature periods, the demand may increase significantly and the system may need to dispatch more conventional thermal generators to provide both electricity and inertia for security purpose, which may also result in the decreasing output of the wind farm.
Yeah, that's a really good point. Although I can't guarantee that the wind farm data is, the wind farms will shut down for a variety of reasons. Sometimes it would be a pure temperature response, and sometimes it will be because of network constraints, or as it's implying here, that there's a market-based reason why they're shut down to provide, so that the other generators can provide that inertia or security purposes. The types of analysis we were doing should have removed a lot of those events. So the goal was to try and identify which were the derating events purely attributable to temperature. And I think operationally, AEMO saw a lot of derating in the 2020 summer that we can confirm was not attributable to network constraints or generation market constraints.
Okay, there's nothing further in the chat. I see Judith's put up our resources. So I guess that kind of brings us to the end of today's webinar. I'd really like to thank Ben and Judith for presenting such an informative webinar, and also to everyone else who's attended for your time and your great questions. A recording of today's webinar will be available shortly on the ESCI page of the Climate Change in Australia website. We would appreciate if you could take the time to fill in a short 2-minute survey on today's webinar. The link's in the chat. Thank you to those who filled in the survey after our last webinar. Those webinar ideas suggested then are being incorporated into upcoming webinars. If you have any questions about today's webinar or the ESCI project, please don't hesitate to contact us. My email address is in the webinar confirmation email. Make sure that you look out for our next ESCI webinar, details of which will be distributed shortly. So thanks again for attending, and we look forward to seeing you at the next ESCI project webinar. Thank you.